Okay, so this section is all about exponential models with differential equations. So we're going to talk about things that have exponential growth and decay. We're going to talk about some like double and half-life problems that I think you guys have seen in maybe chemistry, but just doing kind of a tiny bit of calculus before we just do some actual basic math with it, okay? So I'm going to start out by, if I gave you guys remember this exponential growth and decay formula? You've seen this before, something similar to it. Maybe you've seen PERT before, right? We've seen the PERT formula before. You remember what that's for? Compounding interest, but it's compounding continuously is the PERT formula. Okay, so that's a good example of exponential growth. You've seen that before. And then I know you guys have seen this before in your science classes as well. But I'm going to go ahead and take the derivative of this, and then I'm going to show you how we can work backwards, and I'm going to show you that if you're given something like this, it is basically a shortcut. Instead of doing all of this natural log stuff and taking the integrals and doing the plus c's and solving it this way, there's a shortcut that we can use if you're given something like this, okay? So if I were to take the derivative of this with respect to t, this would be dy dt is equal to, now if I have this a and b, these are both just constants, okay? So when I take the derivative of something to a power with a constant in front of it, we're going to have that constant times that b to the t, but then what am I also going to have that multiplied by?
T?
Not t.
No. Good with T?
If you guys remember on your flashcards, you had ddx of the natural, no, a to the t, where a is a constant. So the derivative of this is just a to the t times the natural log, ran out of space there, natural log of a. Okay, so it's timesing it by the natural log of the base there, so it's going to be the natural log of b, okay? That's one that a lot of us missed on that quiz coming back from winter break when we were doing that derivatives quiz, okay? So, okay, well, a times b to the t, I'm just going to rewrite that as y, because that's what it is, right? So dy dt is equal to y times the natural log of b. And now the natural log of b, like I said, b is just a constant. So this is just a number. So I'm going to give it a variable, and I'm going to give it a specific variable for a reason that I'll explain here very shortly. I'm going to give it the constant k. So I've got dy dt is equal to a constant k times y. Okay, now if you guys remember back to the beginning of this unit, I had some questions up on the TV, and I had you guys write out these different expressions of differential equations with constants of proportionality. Do you guys remember that? If it was like, you would write like dy dt is equal to k times t, or you would write it like k divided by t, or something like that. Do you guys remember that a little bit?
No.
Okay. Well, maybe you were gone. I'm not sure. But we did do it, okay? So that's where this constant's coming back into play, okay? If we worked backwards, we could end up getting to this point, which I will show you here in a second. But basically, this is what an exponential growth and decay function looks like as a differential equation, okay? So normal differential equation, normal exponential growth and decay looks like this. But this is what the differential equation of the exponential growth looks like. Those are a lot of big words, okay? So let's keep on moving here and see how this works. So it says the rate of change of a quantity is proportional to the size of the quantity. So that's your proportionality constant k that we are going to use while we are solving these problems. Okay? Again, this is a representation of an exponential model as a differential equation. Okay? So these first two are just getting some practice writing it down again. So we can choose a variable that we want with respect to time, and then we'll have our constant of proportionality on the right-hand side. So it says, for example 1, the weight of an animal is increasing at a rate that is proportional to its weight. So let's go with dw for weight. So I've got dw over dt is equal to k times, what is it proportional to?
W.
Yeah, the weight. Now, second one, very similar. The only thing that's different, we've got a bacteria population, but it's shrinking at a rate proportional to its population size. What's the difference there?
Divide by the variable.
We're not actually dividing by. We don't know what the constant is, so it is possibly, yes, going to be smaller or negative or a fraction. But we are just going to go ahead and say that let's use a variable p, so dp dt is equal to some constant that is proportional to its population size, so we'll say that's p. Okay, these words of increasing and decreasing or increasing and shrinking, that tells us what kind of exponential function it is. Is it an exponential growth or is it an exponential decay function? So if it's increasing, what do we think that's going to be? Growth. And if it is shrinking, that's your exponential decay. Okay, now we started out by taking the derivative of that exponential growth formula to find my differential equation. Now we're going to work backwards. If you're given the differential equation of an exponential growth, I want to solve for the exponential growth formula in terms of y. Okay, so I've got dy dt is equal to k times y. It says solve that using separation of variables. So before I can take the integral of both sides, I need to get my y with my dy and my dt with my constant k. So I'm going to go ahead and divide by y. So I've got 1 over y dy is equal to k times dt. Now we can go ahead and integrate both sides. If I integrate both sides, I end up getting the natural log of y plus c is equal to, what's the integral of the right-hand side going to give me? Is it k squared? K is just a number. K is just a constant. So it'd be k times t plus c. Okay, let's move that c over to the right-hand side. So I just have one c. So I've got the natural log of y is equal to kt plus c. And then now we want to solve for y. So what am I going to have to do to both sides? E to the power of on both sides. So that e to the natural log goes away, and I'm left with y is equal to e to the kt plus c. Now, can I simplify this a little bit?
Absolutely not.
Okay, if I want to get, let's see, we can do a little bit more. Can I separate those exponents out?
Yeah.
So I got y equals e to the kt times e to the c.
We just did c again.
Yeah. So then I've got y equals c times e to the kt.
Okay.
Yeah. So it's kind of like pert, but instead of pert, it's, I don't know, ce to the kt. Okay. So this is, again, your exponential function, okay? But this right here is your differential equation of the exponential function, okay? So if you are given one or the other, we can just go right in between those two things without having to do all that integration every single time, okay? It's kind of like a shortcut. Can you still do the integration every single time if you want to? Yes, it'll just take a little bit longer. And on this assignment, I want you to practice using the shortcut, okay? So again, it says right here, the solution to your dy dt is equal to ky. The solution to that is y equals ce to the kt, where c is your initial value of the model. Just like when you had your formula y equals per to the t, this was your principal, right? That was your starting amount, okay, when you were talking about compounding continuously. Same thing here, your c is going to be your initial value that you're given, okay? All right, so let's look at this in action here. The first two, you're given differential equations, and you are also given a point, y equals 5, t equals 0, and y equals 4, x equals 0. The thing that's important to note here is the equals 0 piece. That's going to tell me what? My initial condition, right? So this right here is my initial condition. So my initial condition when t equals 0 is going to be 5. So that means that c is going to equal 5, for example, 3. Okay, now I'm just going to look at my formula and plug in all the values that I need to get my y equals ce to the kt. So your formula is going to be y equals, your c is your initial condition, so 5. E will always be there. Now what is my k going to be? K should be next to the variable there, so k would equal 6. And then t I don't know, so I'm going to leave it as time. Okay, because we want the solution for that differential equation. That is my initial condition with the t at 0 gives me 5. Okay. Next one I've got dy dx is equal to negative 3y. And then y equals 4 when x equals 0. So y equals 4 is going to be my what? My c value, or my initial condition, right? So c is equal to 4. So when I'm writing out my equation, I'm going to have y equals my c value, which is 4, times e. And then k, what is my k value going to be in this case? Negative 3. And then if you look here, the variables might change. This variable was a t, which means this variable was a t. What should this variable be in this case?
X.
An x, okay? Oh, I don't know why I wrote it like that. Should be written just next to it, not an exponent. So that's just going from the differential equation back to the exponential function, okay? Okay. Now let's actually answer some questions with this stuff. We've got an animal that weighs 3 pounds at birth, 4 pounds just 3 months later. The weight of the animal is increasing at a rate proportional to its weight. Set up a differential equation for this scenario. How much will the animal weigh when it is 5 months old? So let's start with the very first sentence here. It says the animal weighs 3 pounds at birth. What does that tell me in terms of the exponential growth formula? It's going to be my c value, right? This is my initial condition. So this is going to be c equals 3. If we're talking about weight, okay, we've got increasing at a rate proportional to its weight. So it says increasing, so I know that's going to be a exponential growth, right? And then I can go ahead and write out my formula. So let's say dw for weight over dt is going to equal my constant k times my weight. Okay, so we are now going to change it into my exponential formula, okay? Your exponential formula is normally in terms of x's and y's, right? So we got to be careful here. My y is actually equal to what in this formula? If it's dy, what's my y? W technically, right? So I've got w is equal to, I'm going to write c for a second first. So c e to the k, and then is my t going to stay the same?
No.
Well, for right now, like our variable t is t, right? Yes. Now we're going to actually plug in some information because we know that at birth, the animal weighs 3 pounds. So I'm going to plug in 3 for c. So I've got w equals 3e to the kt. It's kind of like a two-step problem here. I need to first solve for what my k value is, and then I can go and solve for how much the animal is going to weigh at 5 months old. Okay? But in order to do that, we need to use some more information that we were given in the problem. It says 3 months later, the animal weighs 4 pounds. So what could I use? What could I plug into my formula to solve for K?
4 for Y and 3 for T?
Yeah. You mean W, though, for weight? Yeah.
Right.
And then 3 for T. Okay, so if I plug that information in, I get 4 equals 3e to the 3 times K. And then now can we go ahead and solve for K? Yeah, that's just an Algebra 1 problem. Divide by 3, divide by 3. I get 4/3 is equal to e to the 3K. And then to get that exponent down in front, I can take the natural log of both sides. And I got the natural log of 4/3 is equal to 3K. And now if I divide by 3, that is going to be my exact answer for K. Now, did we answer the question yet? No, it says how much is the animal going to weigh when it's 5 months old. So we are going to need to use this constant K and plug it back into my formula with my time equaling 5. What I don't want you guys to do is I do not want you guys to round for K at this point. If you round for K at this point, rounding right here is going to drastically change your answer. So you can do one of two things. You can either use this and plug it in for K up top in your exponents, or you guys know there's a button on your calculator called store, or it actually says STO. Okay, if you look at your calculator real quick, if you type this in and hit enter and then hit stow, it'll hit a little arrow off to the side, and then you can type alpha and whatever letter you want. I would just do K because that's what our constant's going to be. And then that means every single time you hit K, alpha K, enter, it's going to equal that value of K. Okay, so I'll show you that really quick. If you're not sure where to find it, let me know. All right, so now that we found K, we're going to go ahead back and answer our question here because it asks us, actually, how heavy is the animal at 5 months old? So we can go ahead and use our formula here, and we're going to find the weight when my time is 5. Again, this K is stored in our calculator, or we can type the entire decimal out, whichever one you want. It just saves you a few buttons to type. And then when you do that, you should get approximately, now at this point we can round because we're done with the question, 4.846. All right, just another thing again, reminding you guys, if it's growth or decay, growth is when your exponent is positive. Decay is when your exponent is negative if you're given the exponential growth formula, okay? Or those are your K values. So like if your, dy dt has like a negative 5t, okay? That would be an example of an exponential decay because your K value is negative, okay? So doubling in half-life is just as it sounds. If you are doubling your life, that means you are timesing that by 2. And if you are halving your life, that means you are timesing it by 1/2. Yes? So this comes into play because we don't need to know what our initial population or what our initial things are, because if we know we're going to double it or if we're going to half it, we can just set it equal to double that amount or half that amount, and we can just call that a variable, okay? So this example says a population Y grows according to this equation, this differential equation, where K is a constant and T is measured in years. If the population doubles every 7 years, what is the value of K? Well, in your science classes, a lot of the times you do use the notation Y naught. Maybe you haven't seen that before, but it's Y with a sub-zero. Some of us seen that before, yeah? Or you could use a variable, whatever you want, but Y sub-zero kind of stands for your initial condition, so that's what I'm going to use. But I want to change this first into my exponential growth formula. So remember, your exponential growth formula is Y equals CE to the KT. Do I need to change anything between these two, or are those variables all okay? Those variables are all good, right? But currently, as we have it laid out, I have four unknowns. Well, 3 technically, because we know the population doubles every 7 years. So how am I going to solve this if I have 3 unknowns? We're going to have to let something equal a variable, right? This C is my initial condition, right? So what if my initial condition was, let's say, the population was 10, right? Then that means the population, if it's doubled, would be 20, okay? So I'm going to let this equal y sub 0. That's my initial condition, or you could let it equal x. Then that means on the other side, when I double it, I'm going to be left with 2 times y sub 0, right? Or 2 times x if you chose x. And now when I start solving this, oh, I forgot also, what is my t? 7. And now I start solving this here, my y sub 0s, my y naughts are going to go away. And I'm left with 2 is equal to e to the 7k. Can I solve this now for k? Yeah. Take the natural log of both sides. That's going to go away. And we're left with the natural log of 2 is equal to 7k. And so k equals the natural log of 2 over 7, which we can plug into the calculator and give an approximate answer because it asks us what is the value of k and nothing else. So I don't need to worry about approximating. Oh, it should be 0.099. Okay, if this was a half-life problem, it would say that population decreases by half or something like that every 7 years. So this would then equal, instead of 2 on this side, I would have 1/2, right? Because we're decreasing our population. Okay, does that make sense? Questions on that? Okay, your homework is the rest of this, so it's not a separate document. There might be a few questions on here that might be a little tricky. Try them out. You might not have seen an exact type of it, right? But there are 2 at the very end also that are kind of AP style, so if you struggle with those, that's okay. One of them is a calculator problem that we will probably for sure talk about next time. So if you don't get that, that is a-okay. But please, please, please try your best on them, okay? We will go over any questions next class.